Hey, as well, welcome to exercise 11.3, where we take a look at the assignment the assignment problem and bipartite graphs. So what is the assignment problem and what are bipartite graphs? The assignment problem involves finding the best way of matching the elements in two groups, like a group of workers, to a set of tasks the most efficient way or cost-effective way. Long story short, that might sound like a lot, but let's begin by taking a look at bipartite graphs and how it fits in the grand scheme of things. So a bipartite graph will have on the left the people who perform the task. So person A, person B, person C. And then on the right, what sort of job they can do. So it could be task 1, task 2, or task 3. All right. So in a building scenario, it could be like landscaping, concreting, fencing. All right. And then there's usually a cost associated. So to begin with, there's no cost on the tasks on the right. But usually each person who performs these tasks will charge a certain amount of money. Now let's take a look at how we figure out the bipartite graph that shows I guess, the most efficient way that we can cover off all the tasks. So on the right here, we've got ourselves Alan, Ben, Cam, and Dan. They're our 4 workers. The bipartite graph shows a task that each of the 4 workers is able to undertake. If each person must complete one task, find a valid allocation. So what we need to do is we need to just check out which way the arrows are going. For example, Alan here, he can do tasks 1 and tasks 3. So notice how there's only 2 degrees off Alan's vertex. Ben here can do task 2 and task 3. Cam can do all 4, jack of all trades, but Dan can only do 1, and that's task 2. So if we were to just keep the order the same, I mean, you don't necessarily have to, but what happened? No, it didn't connect. Let me reboot. And we're back. Got my little pen tool now. So let's keep it in the same order. So we got Alan, we got Ben, we have Cam and Dan. It's definitely way too spaced out, but I guess we'll just zoom out a bit. All right, so what we want to do is we want to see who, also the tasks. Let me just draw the tasks. Task 1, task 2, so what we want to do is we want to check out who's got the, lowest capabilities of completing the tasks. So Dan is the lowest. He can only complete task 2, and that is the first arrow we want to draw. Okay, so we want to go, Dan, you go and do task number 2. All right, and then we draw ourselves a nice little filled out arrow, and then that's task 2 completed. We basically just want to allocate 1 person per task to get this entire job done. So after Dan, both Alan and Ben have 2 abilities to complete 2 tasks, whereas Cam has 4. So it's logical to say, well, Cam, you go last. We'll plug you in where Ben and Alan can't do a certain task. All right, so Alan can do task 1 and 3. Ben can do task 2 and task 3. Well, let's keep Alan to task 1 since Ben can't do task 1, but he can do task 3, right? So we can say, well, actually, Ben can't do task 2 because that's been taken by Dan already. So now that Alan's taken task 1, which Ben can't do, Ben will have to go to task 3 because he can't do task 4. Right, and then Cam can just basically fill in the gaps since he can do all 4. All right, so Cam here is jack of all trades. Alan's been allocated task 1. Ben's been allocated task 3. Cam here will be just filling in the gaps because he's got the most capabilities. All right, he'll go off and do task number 4 for us. And then that's it. No cost involved. It doesn't say how much it costs yet, but usually we figure out the total cost for the job. But that's example 1. Example 2, we take a look at the matrix form. So whenever we have a bar-pie-type graph, we can represent this as a matrix. So for every connection, if we have, I guess, the workers on the left as rows, and then the jobs as columns, for every connection, we can just put a 1 in the matrix to represent that connection. So example 2 here, 4 workers, A, B, C, D. They all need to be allocated 1 task each. The workers are only qualified to perform certain tasks, and this is indicated in the following matrix. Draw a bipartite graph from the matrix and determine a valid allocation. So we need to draw a bipartite graph. Sorry. And then valid allocation. So basically what we're doing in example 1, but we're drawing a graph first. So let's say we've got A, we've got B, we won't space it out so much this time, C and D. Over here we've got jobs 1, 2, 3, and 4. Okay, so person A can only do job 3. That's easy. Okay, and then person C can only do job 4. All right, so we start here with person A. So you want to do you want to draw the links of the people who have the least capabilities first, or the least variety in the jobs they can do. I don't want to make them sound like they're unskilled, even though they're completely fictional characters with no feelings whatsoever. And then person C can only do job 4. So that's the first 2 we can knock out. Then we can color coordinate these as well. So that's that. That's this. Okay. Well, if you look who's left, B and C. Oh, no, that's not person D. It's person C. That's why it's always good to highlight, to make sure we're making no mistakes. Hopefully you've got rulers as well, which will help you keep your books nice and tidy. Unlike me, who's drawn it freehand. So we've got person B and D left. What you want to see is, well, person D can do 3 jobs. Job 1, job 3, job 4. Person B can only do 2, and he can only, or she can only do 1 and 2. But notice how D can't do number 2. So that's why B has to go and do job 2, since if we allocate, well, we actually can't physically allocate job 2 to person D. So here we've got person B going to do job 2. That is cyan. Well, that turns a green. And then lastly, we've got job 1 left over to the person who's got the broadest capabilities, and that's person D. All right, and we can say this is going to be the pink color. And it goes through everybody. Oh, that makes a funky intersection. But I think you get the gist. Everyone's been allocated a job, and you always start with the person who has the least qualifications in doing certain jobs. All right, so determine a valid allocation. Oh, already, that's what we just did. So the full bar pie chart graph, no, I've done it in the wrong order. Well, so that's a valid allocation. I guess that was easy to do. Okay, so person A does job 3. Person B does job 2. Person C does job 4, and then person D does job 1. All right, so that's the valid allocation. Damn it. Yeah. Again. Oh, okay, that'll do. For the full bar pie chart graph, which we should have probably done first, but it doesn't matter. We just need to make sure we connect every person's capability to every job that they can do. All right, for example, if we have A, B, C, and D jobs 1, 2, 3, and 4. Okay, A can only do 3. And we want to put the arrow in the middle. B can do jobs 1 and 2. So we connect 1 and 2. C can connect to job 4 only. And then D can get to 1, 3, 4. So 1, 3, and 4. You can see why the VCAA will be reluctant to make you draw stuff, because it can come out pretty messy like what I've done here. So that's why they'll usually give you the bar pie chart graph and make you figure out the allocation, like so. That's usually what they'll ask. But there's an optimum way to assign people. So once we start putting values on these jobs, for example, person A might do job 3 for $50. Person B might do job 2 for $40 and job 1 for $30. We start to consider the financial problem of finding the most optimal way we can get a job done, the cheapest. So this is where row and column reduction comes in. When we have 3 people, for example, in example 3, where we've got 3 people competing for 3 jobs, and they've all got their own sort of price or time, we can figure out which one is going to be the cheapest or the quickest. So here we are talking about the time in hours. And we've got 3 workers, A, B, and C, that need to be allocated to 1 task each from tasks 1, 2, and 3. The time in hours that each worker takes to complete the task is shown in the table. If the tasks must be completed in the minimum time, find how the tasks are assigned. So this method is called row and column reduction, where we slowly filter out, I guess, the most efficient people for each job. So what you want to do is first step. So step 1. I tried drawing these tables, it turned terribly, so that's why I kind of just screenshotted. So step 1, find the lowest value in each row and subtract the other values with it. So what does that mean? If we grab out our highlighter, we've got 3 rows representing 3 people. So person A can do job 1 in 8 hours, job 2 in 10 hours, job 3 in 9 hours. Okay, we find the lowest, and that's 8. We then go and subtract this entire row by 8. So 8 take away 8 will get us 0. And then 10 take away 8 will get us 2. 9 take away gets us 1. The next part is we take a look at person B. He or she is most efficient at job 3. Okay, so we subtract every other job 1 and 2, by 7. So 9 take away 7 gets us 2. 11 take away 7 gets us 4. 7 take away 7 gets us 0. And then we go and take a look at person C. Person C, we've got ourselves 7, 9, and 8. So job 1, person C is the most efficient at. We subtract the entire row by 7. So 7 takes 7, 0. 9 takes 7, 2. All right, 8 takes 7 is 1. After that, what you'll notice is we've got ourselves a bunch of rows and columns with zeros. Okay, so step 2 is for all the, let me just write it first. So step 2, once we've done, this is what we call row reduction. That's step 1. Step 2, we find columns with non-zeros. Okay, so while I'm writing this down, see if you can find the column from above with non-zeros. All right, so we've gone from there to here to here. So find the columns from here with non-zeros and subtract the lowest value in that column with the others. Okay, so previously we did a row reduction. This is what we call the column reduction. All right, so what you'll notice here now is there's only one column. There's only one column without a 0. Okay, so we've got 0, 2, 0 in column 1. Column 2, we've got 2, 4, and 2. So what we notice is we've got 2 sets of 2s that are going to be the equal lowest. So we subtract every number in column 2 by 2, and we leave the ones with zeros alone. Okay, so 2 take away 2 gets us 0. All right, 4 take away 2 gets us 2, and then 2 take away 2 again gets us 0. Okay, so column reduction, let's highlight this in purple. And previously we had a bunch of colors. I don't like that. Let's make row reduction. So all these will make it yellow. All right. Okay, so we did row reduction in yellow, column reduction in purple. Okay, and then the result we get is this. All right, so step 3. We want to draw lines through each column and row, or row and column with zeros to see if we need to do the Hungarian algorithm. Now you're probably wondering, what the hell is the Hungarian algorithm? The Hungarian algorithm is when there are essentially not enough lines to cover the number of rows we have. Okay, so what you notice is we've got 3 rows, okay, and we've got 3 lines. All right, so we've got 3 lines. So draw lines through the zeros. Okay, we've drawn lines through all the zeros. We've got a 0 in column 3 as well. And if the number of lines that we draw match the number of rows, okay, we have a solution. So so how do we decide if lines equal rows? No need for Hungarian. All right, if lines, so the lines we're talking about are the ones that go through the 0. All right, so if there's I guess any sort of zeros, okay, we draw the rows first. And then if there's zeros in any columns that we've missed, so the first 2 lines we would have drawn are A and C, and then we notice there's a 0 in B still left, okay, then we need to draw a column line to match that, to cover all the zeros essentially. So if lines do not equal 0, rows, then Hungarian algorithm needed. All right. So what we found here is actually, what did I do? What we found here is actually the most efficient way for the workers to complete the tasks. Okay, so all it's saying here is okay, we've got person A, person B, person C. Anytime they have a 0, they can do that job. Job 1, job 2, job 3. So A can do 1. A can also do job 2. B can do job 3. And then C can do jobs 1 and 2. And so because there's no necessarily, oh no, it does ask. And then it asks the minimum time it takes to complete. So we know A would take 8 hours to do job 1. A would take 10 hours to do job 2. Again, do this in pencil because we will rub out some lines. B can do job 3 in 7 minutes. Or is it out 7 minutes? What units are these? Does it say? Time in hours. Yeah. So B can do job 3 in 7 hours. C can do job 1 in 7 hours and job 2 in 9. So 7 and 9. Okay. So now that we've got literally the bipartite graph drawn in full. Come on. Where is it? Here it is. So now that we've got everything drawn in full, we want to rub out the inefficient ones. For example, A can do jobs 1 and 2, but is most efficient in job 1. All right. And C here can do jobs 1 and 2 as well. But what you notice is, I guess C is more efficient at both jobs 1 and 2 than person A. So what we want to do is we want to take the absolute smallest. Now, obviously, person B can do job 3 only, so that's the easy line to take. What we want to do is we want to take the absolute lowest. So since A and B share jobs 1 and 2, we want to take the absolute lowest. So C is the most efficient at job 1. All right. And that would take A out of contention to do job 2. So if we went with that option, that would be 7 hours for C to do job 1, and then A would have to do job 2, which is going to be 17 hours in total, because 7 plus 10. Or we could go 8 and 9. That still adds up to 17, doesn't it? Okay, so we've got a weird coincidence where both A and C have sort of the same job outcome. So let's rub out. Let's rub out C. So we go with 7. So C can do job 1. And then A can do job 2. All right. So therefore 24 hours. So 10, 17, 24 is going to be most efficient. Most efficient time. Okay. Whew, all right. Let's move on to the Hungarian algorithm. All right. So the Hungarian algorithm is an extension to the row and column reduction method when we get a situation where these lines that we draw through the 0 don't equal the number of rows we have. For example, if this example that we just did had only 2 lines and this B row didn't have a 0, we would have to proceed to the Hungarian algorithm because we would have 2 lines compared to 3 rows. Now, this little extension is just essentially 2 extra steps to what we just did. So let's take a look at the example before we, it's hard to read all this and make sense of it without an example. So let's go down and do a example. All right, so we've got 4 workers here, A, B, C, and D, and this time they all provide quotes for jobs 1, 2, 3, and 4. Their quotes are shown in the matrix where the rows represent the workers A, B, C, and D, and the columns represents the jobs 1, 2, 3, and 4. So when we talk about quotes, it's not an English quote, it's talking about dollars. That's a terrible dollar sign. They're talking about dollars. Okay, so what we want to do is we still want to do the row and column reduction method. Okay, so step 1. Row reduction. All right, and we can row reduce straight from this matrix here. Okay, so looking at each row, the smallest number for row A is 15. Okay, and then we go on and subtract every single number in row A by 15, and then that's going to give us 0, 24 take 15, 9, 40 take 15, 25, 21 take 15, 6. And then we look to row B. Smallest number, 18. Okay, so 24 take 18 is 6. 18 take 18 gets us 0. 19 takes 18 gets us 1. 20 takes 18 gets us 2. Okay, but notice how the smallest number now is all turned into 0. Row C, smallest number is 13. So 28 take 13 gets us 15. 13 take 13 gets us 0. 30 take 13, 17. 22 take 9. 22 take 13 is 9. Lastly, we've got 10 as the smallest number for row D. So here we go 10 take away 10, 0. All right, 18 take away 10, 8. 17 take away 10, 7. 13 take away 10, we've got 3. Okay, so that's row reduction done. Step 2, we do a column reduction. Column, again, this is just the same steps as we wrote in the previous example, but I'm not writing the full paragraph. So column reduction, okay, for non-zero columns. For non-zero columns only. Okay, so let me just double check what color I used. I used purple. All right. So column reduction here, we have to find the non-zero columns, and we have ourselves the 3rd and 4th column. Okay, so the column, this entire column here and this entire column here, there's no zeros. Okay, so what we need to do is we need to go and locate the smallest number in the column and subtract every other number with that small number. And for column 3, it's number 1. For column 4, it's the number 2. So 25 take 1 gets us 24. 1 take 1 gets us 0. 17 take 1 gets us 16. 7 take 6 gets us 6. Here we've got the number 2 for column number 4. 6 take away 2 gets us 4. 2 take away 2 gets us 0. 9 take 2, 7. 3 take 2 gets us 1. Okay. So from here, we go into step 3. Draw lines over rows and columns. Damn it. Can't spell the word column. Draw lines over the rows and columns with zeros. So you've got, I think I use light blue. We've got a row here in B with 3 zeros. Now, if it just has 1 0, you got to draw the entire row. Okay, so it doesn't matter how many zeros it has. If it just has 1, draw a line through the entire row. What we notice is that's it for rows. Okay, we then have to do columns. So what have we got? Column 1 and column 2. Alrighty. So one thing I do want to mention is, I think I might have missed it here. When we draw lines through each row and column with zeros, we want to do this with the least number of lines. So draw through each row and column with zeros. This is probably too much. Let's amend some of the notes. Okay, we want to draw with the least number of lines. Okay, so I think I might have said if there's a 0, you got to draw a line through it. No, we want to do it with the least number of lines. So draw lines over rows and columns with zeros, using the least. Okay, so the reason being is if we were to draw lines over every single 0, then we'd have lines over everything, and that's not going to help us. Okay, so the most efficient way to draw the least number of lines with a table like this is to strike through the one with the most zeros, so the row or column with the most zeros. So that'll be row B. And then any other column that has multiple zeros, which is row 1 and 2. And then if there happens to be other zeros left over, then we don't need to do in Hungarian. But because we have 3 lines and 4 rows, we need to proceed to the Hungarian algorithm. Okay, so here, what's unfortunately happened is we need to proceed to step 4. Okay. So, if rows don't equal lines, we need to add 1 to each number. Each number covered by a line. So if the line overlaps, if the line crisscrosses, add 2. So what does that mean? We have crisscross intersections here at B1 and then B2. So with 6 and 0, we need to add 2 instead of 1. All right, so notice how all these original crossed out numbers have all been added by 1. Now the crisscross. Let's use the crisscross section is, oh no, what color can we use? This? Yeah. We'll just circle it. The crisscross section is the 8 and 2. All right, so we'll circle this part. So if the line crisscrosses, add 2. All right, so the 6 and 0 has been added by 2. Cool, so this is the start of the Hungarian. We've added, seems like we go backwards, like we've added all the line covered numbers with 1 and 2, if it's been covered by a singular line or 2. And so the last step, step 5, is going to be essentially a row reduction to see. So row reduction again. Okay. So what you notice is, let me just check what color row reduction was yellow. What you notice is we've got now 0, 0 here, 0 and 0, and they correspond to, I guess, this. This and this. Damn it, the colors kind of merge. Okay, so step 6. We draw lines again through the zeros using the least number of lines. So draw lines through the zeros with the least number of lines. And now what you see is we've actually got all these zeros, right? So we have to strike a row for B because there's 2 zeros. We have to strike a column line for 1 because there's 2 zeros. And then we either have to go vertically or horizontally through C or 2 to cover this C2 0. And so that means we have 4 lines. It equals the number of rows. Now we can proceed. If we zoom out, we can proceed to the last part of the question, which is determine the best allocation of workers that minimizes the quote. All right. So let's draw this. we've got worker A, B, C, and D. We've got job 1, job 2, job 3, and then job 4. And every 0 represents which job is going to be an efficient one for the worker to do. A has only one job to do number 1. D has the ability to only do one job as well. B can do 3 and 4. Three and 4, and then C can do job 2. All right, let me just stare at this for a sec. So we've got 2 people can do job 1. Here we go. This is a 0 that we've missed. Haha. Yeah, I was missing something. So that's more like it. So D can do job 1 and 4. Now we need to put some values on, I guess, these lines. Okay. So A doing job 1 is $15. B doing 3 and 4 is $19 and $20. C doing job 2 is $13. What's the other job C has to do? C can only do job 2. And then D can do jobs 1 and 4. So D can do job 1 for 10 and 13 for 4. All right. So now it's time to remove some of these lines. So person A can only do job 1. So that eliminates this line from D. That leaves D only able to do job 4. So that eliminates this line from B. And then that's sorted itself out. So A does job 1, B does job 3, C does job 2, and then D does job 4. It says, determine the best allocation of workers that minimizes the total quote. All right, so yeah, therefore, A does job 1, B does job 3, C does job 2, and then D does job 4. How much are all this? So find the cost for the 4 jobs. Well, A to 1 is $15. B to 3 is $19. C to 2 is $13. And then D to 4 is $13. So total, what's that? 13, 13, 26 plus 15, 31, 41, 41 plus 19, 50, 60, $60. All right, for the cost of 4 jobs. So there it is. That's the Hungarian algorithm for you. Okay, it's just an extension to the row and column reduction method when the number of lines that are covering the 0 in the most efficient way doesn't equal the number of rows, and then you have to add 1 to the zeros and all the numbers covered by those lines, and then 2 for crisscrosses, to make sure that we continue with the row reduction again to get more lines. And that's it for Hungarian. Let me know if you have any questions, and that's all for Friday. Thanks, everyone.